Today we're going to continue talking about the fundamental theorem of calculus. Let's open up with just stating the fundamental theorem of calculus and interpreting what it means, because we have two parts, and that's just the fundamental theorem of calculus going both ways, connecting the two big ideas. So we need a continuous function on a closed interval, and then any value from that interval, and it could be one of the endpoints, A or B. So the first part of the fundamental theorem of calculus says that the definite integral from A to B of f prime of x dx is f of b minus f of a. That is, we can evaluate a definite integral using an antiderivative. We want to evaluate a definite integral, and we can use we look at the endpoints. We look at the antiderivative at the endpoints of the interval. So f prime is the derivative of f, and that means that f is the antiderivative of f prime. So just make a note of that. F prime is the derivative of f. F prime is the derivative of f, and that means that f is the antiderivative of f prime. So f is the antiderivative of f prime. That's the relationship between derivative and antiderivative. So what this first part of the fundamental theorem of calculus says is that we can evaluate a definite integral using an antiderivative. The second part of the fundamental theorem of calculus states that capital F of x, defined to be the definite integral from c to x of f of t dt, is an antiderivative of f of x. So the interpretation here is that we can construct an antiderivative using a definite integral. So here we're constructing an antiderivative using a definite integral. So that's the two directions. We can evaluate a definite integral using an antiderivative. We can construct an antiderivative using a definite integral. So to make sure our parts are named down here, little f is the derivative of capital F. So little f is the derivative of capital F. And, well, just like it says on the tin, capital F is an antiderivative of little f. So we're constructing an antiderivative using a definite integral. Some things that we want to note that are also being stated in this fundamental theorem. The big one overall is that differentiation and integration are almost inverse operations of each other. Differentiation and integration are almost inverse operations. The reason they're not exactly inverse operations is that the derivative of a constant is 0. So when we integrate, we get this unknown constant of integration. We lose information because the derivative of every constant is equal to 0. So when we're integrating, we don't know what the constant was. In the same way that the function x squared is not invertible. 2 squared is 4, and also negative 2 squared is 4. So if we try to apply the inverse function to 4, it's either 2 or negative 2, and that's not a well-defined function. We need two functions. One for the 2, one for the negative 2, because x squared is not invertible. So in the same way, differentiation and integration are almost inverse operations, but not quite. because the derivative of every constant is 0. So almost because of the plus c thing. So that's why I say they're almost inverse operations of each other. The other things that we get when we to interpret our fundamental theorem of calculus, it's important to be able to construct antiderivatives because not all functions have what I call nice antiderivatives. That is, antiderivatives that are finite combinations of elementary functions. We don't have nice antiderivatives. That is, we don't have, the antiderivative is not a finite combination of elementary functions. To write the antiderivative, we have to either use an infinite combination of elementary functions or a finite combination of non-elementary functions. Elementary functions are all the functions that you've encountered this far in your mathematical career. So when we're forced to construct an antiderivative using the second fundamental theorem of calculus, we are usually constructing a non-elementary function. The other thing that we get is from the first part, in that the definite integral of the rate of change of a function on an interval is the amount of change in the function on the interval. That's just reading that first line of the fundamental theorem of calculus, where f prime is the rate of change of the function f. So the definite integral of a rate of change the definite integral of the rate of change of a function is the total change in the function on the interval. The definite integral of the rate of change of a function is the total change in the function on the interval. F of b minus f at a. F of a is where the function started. F of b is where the function ended. We're just looking at the difference between those two values. This we connected to old ideas where we talked about the direction of the function, determining the direction of the function by the sign of the derivative. If the derivative is positive, then the function is increasing, and the area tells you how much. If the derivative is negative, then the function is decreasing, and the area tells you how much. Another important aspect of interpreting the definite integral is to look at the units of the definite integral. So another good way to determine the units of the definite integral it's going to be the units of f prime of x multiplied by the units of x. So whatever f prime, the function that you're integrating, whatever the units of the function you're integrating, you multiply those by the units of x, and those will give you the units of the definite integral. And that could be a way that we interpret what's going on with the definite integral, what the definite integral is telling us. Another important thing to note about this is that applications of integration are all of our applications of multiplication, because the units of our definite integral are just the units of our function and the units of our variable. Any application of multiplication can also be an application of integration. Anywhere we're using multiplication is a place we might have to use integration if one of the factors is variable. Applications of multiplication are applications of integration. This is for when things get difficult and we start wondering, when am I ever going to need to know this? When is this applicable in some other situation? And when the question is, when is integration going to be applicable? It's going to be applicable wherever there is multiplication, because integration is multiplication, but one of the factors is variable. Integration is multiplication in which one of the factors is variable. And when one of our factors is variable, oh, we should be more specific. Integration is multiplication in which one of the factors is continuously variable. Integration is multiplication in which one of the factors is continuously variable. If you recall how we dealt with this, we made our function, our continuously variable factor, we just made it constant for a little while so that we could use multiplication, and then we added up the results. So integration is just addition. Because addition is what we do when our terms are not the same. So in that sense, integration goes all the way back to the beginning when we first started learning operations on numbers. The first operation on numbers that we learn is addition. And we learn that we only add things that are the same, and when we add them, it doesn't change what they are. $3 plus $2 is $5. We can add the 3 and the 2 to get 5 because 3 and the 2 are both dollars. we learned that multiplication is repeated addition. If I have 3 plus 3 plus 3 plus 3 plus 3, since all my terms are the same, I can summarize that and say 5 times 3. And so when we learned our times tables, we were learning a shortcut to just doing 3 plus 3 plus 3 plus 3 plus 3. Because multiplication is just repeated addition. And then we learned our exponents. If I had 3 times 3, I call that 3 to the second power, because exponents represent repeated multiplication. Those are our original operations on numbers. Integration is just a generalization of that, where one of the factors, instead of saying 3 times 5, I'm saying f of x is continuously variable, so I integrate one factor with respect to the other. Finally, your arithmetic class has come full circle. It only took like 14 years. These are the ideas that we want to have running around in our heads while we're doing other calculus stuff. These are ideas. Knowing all the stuff in my list of things to know about integration will not help you find antiderivatives. That's a separate skill that we need to develop. But while we're developing that skill, these are the things that we want to keep in mind. We want to remember our fundamental theorems of calculus. We want to remember how we can interpret those fundamental theorems of calculus. We want to remember some of the big ideas about integration and what the fundamental theorem of calculus is telling us. And we want to think about where those ideas come from. Any questions? All right, let's talk about some technical business. One of the things that we'll need to be able to do, finding antiderivatives. We're going to spend a lot of time finding antiderivatives. And then next semester, I'm going to say, hey, let's find some antiderivatives. And y'all are going to be like, oh, didn't we do this last semester? And I'll be like, oh, yeah, but wait, there's more. So usually when we do a math class, we do a thing in one semester. And then if it shows up again in the next semester and the teacher's like, oh, we're going to practice this some more. And you're like, oh, whatever, we did that last semester. That'd be like going to basketball practice one week and the coach being like, oh, all right, let's practice our free throws. And you'd be like, oh, we did that last week. So when your coach is like, oh, we're going to practice some free throws, it's not because you haven't done it before. He's kind of like saying, hey, you aren't very good at it. We should practice it some more. And that's what's going on here. Like we do antiderivatives and then more antiderivatives. Then next semester, you're thinking, I'm glad them antiderivatives are done. Next semester rolls around, I'm like, oh, no, we're going to do some antiderivatives. All right. First thing to remember about antiderivatives. All of your derivatives are now indefinite integrals or antiderivatives. All your derivatives are now also antiderivatives. all your derivatives are also now antiderivatives. So everything that you know about derivatives are now going to be things that you know about antiderivatives. So for example, we know that the derivative of any constant is equal to 0. And so that means the antiderivative of a constant dx, we're going to think about the antiderivative of 0 dx being some constant. This is what we call our constant of integration. This is the constant of integration, and we attach it to every indefinite integral. So we just tack a plus c onto all of our indefinite integrals. Otherwise, I take off a billion points, and that takes you all the way back to kindergarten math. And you have to learn addition all over again. It makes sense. This is a question of plus. You have to put a plus c, so you have to go all the way back to when you first started learning plus. I actually don't know when that takes place. Like all of your practical math that you need to function as an adult, once you know how percentages work, and you can do like your operations, addition, multiplication, and you know what percent means, you're kind of okay. You're kind of set from a practical standpoint. You're in the optional math section now. You're doing this class for fun. So let's write down some more derivative rules and then rewrite them as indefinite integral rules or antiderivative rules. So the derivative of a linear function, let's say kx is equal to k. The derivative of 5x is equal to 5. The derivative of 10x is equal to 10. The derivative of pi x is equal to pi. So the integral of a constant is going to be kx, and then we put plus c because that's k plus 0. So the plus c always shows up. We had some other important rules. We know that the derivative of a power function, let's say x to the n, we multiply by the exponents and then we subtract 1 from the exponent. So if we invert this process, the integral of a power function, we add 1 to the exponent and then divide by the new exponents. And then we put plus c because the plus c always shows up. Now you may notice that this is not going to work if n is equal to -1, because then we'd have to divide by 0, and we're not allowed to divide by 0. The math cops show up, and then they break down your door. You get arrested and taken to math jail. It's a whole big thing. So this only works if n is not -1, because we can't divide by 0. But that's okay, because the derivative of the natural log of x, I spelled L wrong. I had to draw one vertical line like that, and I spelled it wrong. The derivative of natural log of x is 1 over x. So in the case where n is equal to -1, I don't use the add 1 to the exponent to divide by the new exponent thing. The integral of x to the -1 is natural log of x. Plus c, because the plus c always shows up. There's an extra piece that we need with the integral of 1 over x dx equals natural log of x. And it comes from the fact that 1 over x and natural log of x have different domains. 1 over x can apply to any x that's not 0. Natural log of x requires that x be positive, strictly positive. It's not just the no 0 thing. Natural log, we can't have the natural log of a negative number. So to make the domains match up, the integral of 1 over x dx is natural log of absolute value of x. We need absolute values when we integrate 1 over x just to get the domains to match. So I want the antiderivative to share the same domain as the 1 over x. So the integral of 1 over x is the natural log of absolute value of x. All we're doing is turning around our derivative rules and turning them into antiderivative rules and then remembering them all. Either because we have to sit down and memorize them, which sounds awful because it would be, or because we just start remembering them. So we know some derivatives of trig functions. The derivative of sine x is cosine x. So the integral of cosine x dx is sine x plus c. The derivative of cosine x is -1 times sine x. So the integral of sine x dx is negative cosine x plus c. We know the derivative of tangent is secant squared x. So the integral of secant squared x dx is tangent x plus c. We know that the derivative, I'm going to do the slightly fancy one, of e to the k times x is k times e to the kx. So the integral of e to the kx dx is 1 over k e to the kx plus c. If we just think about this derivative of e to the kx is k e to the kx, if I multiply both sides of this equation by 1 over k, which I can do because the derivative is a linear operator, then the k will cancel out with the 1 over k. So that's why the 1 over k shows up over here. When we differentiate, it's going to be a k. When we integrate, it's going to be a 1 over k. Okay? K. Okay? Okay. Any questions? There are many more, and we have to remember them all the time. So, like selling an album on television, plus many more. I don't even know if they make these CD sets anymore. Like AM Gold, and then they like make a CD and they list all the songs on the CD, and they just like they're scrolling up the screen, and it's all these hits that your parents used to listen to. And then at the end, it's like all plus 3 more. And it's like, oh, dude, you couldn't just list 3 more? That's like just 2 more lines. Instead of saying plus 3 more, write the first of the last 3, and then just put in 2 more lines for like the last 2 of the last 3. And this is an album with like 50 songs on it. Just speed it up. Go from 48 in that time to 51 in that time. It's hardly a change, right? Just speed up the scroll a little bit and list all of them. Because it's not like anybody's watching this anyway. You know what I mean? Meanwhile, I'm the only person old enough to remember when they would advertise mixtapes on television. No. And I'm kind of wondering if mixtapes are only known about because of Guardians of the Galaxy. Are mixtapes a thing? Mixtapes are what we used to have before like Spotify playlists. I guess that's the upgrade. That's the modernization. All right, so the skill that we need to build is finding antiderivatives of functions or indefinite integrals. So when we say finding antiderivatives, we might also say finding indefinite integrals. Antiderivatives and indefinite integrals are interchangeable enough that we'll just use them both in the same way. So now we enter the death by examples phase. So since the last one we did was this e to the kx business, we've got well, let's integrate an e to the kx. What we have to do is make sure that we separate out what role each number is playing. In this example, integral of 5e to the 3x, 3 is taking the role of the k, 5 is just a constant multiple. So it's important to recognize the roles that each of the constants play. 5 is just a constant multiple. Or a constant factor. Three is the k from the formula. So the constant multiple just hangs around. The integral of e to the 3x is 1 over 3 e to the 3x plus c. So we're saying that 5/3 e to the 3x plus c is an antiderivative, is the general antiderivative of 5e to the 3x. If we want to check, we take the derivative of our answer. So the derivative of 5/3 e to the 3x plus c, the derivative of 5/3 e to the 3x is 5/3 times 3e to the 3x plus 0. The 3's cancel, and we end up with 5e to the 3x, just like we were supposed to. So here is the game that we want to play. We want to take all these derivatives and remember what they are by doing thousands upon thousands of problems. Any questions? You need to be prepared for integration battle because it can happen at any time. It's like learning self-defense, but instead of someone using like physical violence against you, they threaten you with an integration off. Anytime someone challenges me to a duel, and that means I get to choose the weapons, I always choose integration because I'm very confident in my integration abilities. You know what I mean? So that's what we're going to work on this week. We're going to work on finding antiderivatives. Here's a start of the derivatives that we just need to know. This is your new times table for this topic. This is just stuff that you have to know now. I can't fit them all on one page, can I? No, just barely didn't. Yeah, kind of fits. There we go. This is just stuff that you know now. All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day. Thanks for playing.
Thank you.